Lesson 97 began with a review of servo motor theory. Servo motors do not rotate continuously. Rather, they turn to a given position and hold that position until commanded to turn elsewhere. The servo motor control signal is a single pulse with a 20 millisecond period. The pulse width of the control signal determines the servo position. 0.5 milliseconds giving a servo angle of 0 degrees, and 2.5 milliseconds giving a servo angle of 180 degrees. The servo motor position responds linearly between 0.5 milliseconds and 2.5 milliseconds. Our assignment in Lesson 97 was to create a state machine program that would position a servo motor at 90 degrees with no Python code in the main while true loop. A 90-degree servo angle requires a pulse width of 1.5 milliseconds. We'll be using microsecond values in our state machine calculations in order to avoid fractional millisecond values. So our period set point is 20,000 microseconds, and our pulse width set point is 1,500 microseconds. The heart of this program will be a counter with a maximum value of 20,000. The state machine frequency will be adjusted such that each count takes 1 microsecond. So one complete cycle through the counter will represent 20,000 microseconds or 20 milliseconds, the period set point of the servo control signal. As the counter executes, comparison instructions will determine whether the control bit should be high or low, creating the 1,500 microsecond pulse width that moves the servo to 90 degrees. Our first challenge is to load the relatively large period and pulse width set points into the state machine without Python involvement. The ISR, OSR, X and Y registers can hold 32-bit numbers, so space is not an issue. The problem is that the set command has a 5-bit maximum, preventing us from simply setting our set points. The in instruction is the solution. It will shift n bits from the source register into the ISR register. Let's use the pulse width set point as an example. The binary equivalent of the pulse width set point is shown here. We start by breaking the set point into 5-bit segments. Working from the most significant segment to the least significant segment, we set the X register and use the in instruction to shift that segment into the ISR, as shown here. Once the set point is in the ISR, we can move it wherever it's required. Another smaller challenge is to select a decrementing or an incrementing counter. A decrementing function is built into the PIO assembler. In Lesson 90, we learned how to create an incrementing counter. I find the incrementing counter is more intuitive and possibly easier to explain. However, the decrementing counter uses fewer instructions and may be preferable in the constrained instruction space of the state machine. Is there a performance difference? Which should we use for this assignment? That remains to be seen. The incrementing counter sets the control bit high at a count of 0, then starts counting up. When the count reaches 1,500, the control bit is reset and the count continues until the period is complete at 20,000 microseconds, at which point the whole process repeats itself. The decrementing counter starts counting at 20,000, resets the control bit, then counts down. When the count reaches 1,500, the control bit is set and the count continues down until the period is complete, at which point the control bit is reset and the whole process repeats itself. We'll compare both approaches. Here's the code. As usual, we start with imports. We import pin because we use the pin statement in the PIO instantiation. We import RP2 because we're going to be programming a state machine. The @RP2 decorator on line 4 specifies that we'll be using set instead of out, and we'll start with our output pin being low, and we're setting the shift direction parameter to right. Because the set servo position function definition follows the @RP2 decorator, it will be interpreted as assembler code, not MicroPython code. The set servo position function contains the assembler code for our counter. We'll return to that shortly. Line 37 instantiates state machine 0 by specifying the state machine number, the name of the function containing the assembler code, the operating frequency, and the least significant GPIO output bit. We need each pass through the counter to take 1 microsecond. We adjust the frequency parameter in the instantiation statement to accomplish this. There are 7 executable statements in the counter. Labels, wrap, and wrap target statements are not executable. Other executable statements, like line 22, are only run once in the 20,000 cycles of the counter and can be ignored without causing a detectable error. Each pass through the counter must complete in 1 microsecond, so each of the 7 executable statements must execute in 1/7 of a microsecond, or 0.142857 microseconds. Therefore, we set the frequency parameter to 1 over 0.142857, which is 7 megahertz. Line 38 activates the state machine. The remainder of the program is a try-except clause containing an empty while true loop and a Control-C exception, which will deactivate the state machine and message the user that the program has stopped. The assembler code starts by loading the pulse width set point into the ISR using the in technique described earlier. Once the pulse width set point is loaded into the ISR, we copy it from the ISR to the OSR for safekeeping and copy null into the ISR to clear it for the next operation. Here we use the in technique again to load the period set point into the ISR. Now that the period and pulse width set points are stored in the ISR and OSR for safekeeping, we begin to create the control signal by setting the output pin. We copy null into the Y register to clear any data left over from prior cycles. We then increment the cycle count using the invert, decrement, invert technique learned in lesson 90. If you don't know what that's about, there's a link in the description below. At this point, we copy the pulse width set point to the X register, then compare it to the current count to determine if the control pulse is complete or not. If the control pulse is complete, we reset the output pin. Whether the pulse is complete or not, we end up on line 33, where we copy the period set point from the ISR to the X register. On line 34, we compare the period set point to the current count, which is in the Y register, to determine if the period is complete. If the period is not complete, we continue counting. If the period is complete, we wrap back to wrap target and start another period. The decrementing counter logic is the same as the incrementing counter logic up to line 21. You will notice that the decrementing counter only has 2 executable statements compared to the 7 in the incrementing counter. This changes the frequency calculation. 2 executable statements must complete in 1 microsecond, so each statement must take a half microsecond to execute. This requires a frequency of 2 megahertz, as you can see on line 37. As described earlier, the decrementing counter starts by setting the X register to the period set point, the Y register to the pulse width set point, and resetting the control bit. It then begins decrementing. When the current count hits 0, in other words, we've completed a period, execution falls through line 26 to line 27, and the counting loop restarts. But before the current count hits 0, line 26 sends execution to the check pulse width label, and the current count is compared to the pulse width set point. If the current count is not pulse width, we simply carry on counting. If the current count is pulse width, we set the control bit, then carry on counting. Here's a comparison of how they work. Here we see an oscilloscope trace of the control pulse generated by each counter. Both counters generate a steady pulse, with a 1.5 millisecond pulse width. Both counters also generate a steady period of 20 milliseconds. Here's how they operate in real life. Both counters seem to do the job. If I had to choose one, I would probably choose the decrementing counter because it is shorter and doesn't require such a high frequency setting. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.